And we'll go from this slide. Like I said, we've already done part of the slide before, but the last part we haven't. But before we get to that, let me go over a couple of things with you. Do any of you go to the Birmingham campus occasionally, frequently, at all? None of you? Oh, you do. Okay. If you ever eat over there or do anything else in the Leon Kennedy Student Center, from what they say here, that is now closed. All the things that were in Leon Kennedy Student Center are now in the new Academic Success Center. Okay? Y'all know that new building they've been building is now occupied. That includes the cafeteria. As far as I know, it includes the bookstore. As far as I know, it includes the Space Center. As far as I know, even the police department. I don't know that for certain, but I assume they moved over there too, because they said here in this email we got yesterday, please note that the Leon Kennedy Student Center is closed. The cafeteria is now operating in the Academic Success Center. Okay. They also publish an administrative calendar every month. Most of the times I don't print it, but this one had enough things on it I thought might be worthwhile. One thing they left off of it, does anyone know what tomorrow is? Hell Day. All right. Okay. And here's Maya. Okay. Now, what that means, among other things, is you're liable to hear a fair amount of music. I think you'll see a fair amount of food. I believe they'll have a fair amount of games going on of one nature or another. Usually it's not quite as big a deal on this campus as it is on the Birmingham campus, but they do have quite a few things usually going on over here too. And it's a good day to wear your Lawson State paraphernalia, so if you want to do that, please do that as well. As far as I know, classes generally will not be interrupted. You'll just do that in between classes, before class, after class, whatever. Okay? Now, there are a few exceptions. One student told me yesterday that his either English or speech instructor said that don't bother coming to class Wednesday. And I believe that's because that instructor is based on the Birmingham campus, and he probably had some things that he had to do over there as part of L Day over there. In general, classes will go on as scheduled, as far as I know. I haven't seen anything to the contrary. All right. According to this, online registration for summer term opens next Monday, though I have seen some students are pre-registered for some summer classes already. Not very many, but a few. But officially it opens Monday. Okay? Now, this one will affect us just maybe a little bit, but I kind of doubt it at all. Next Thursday, not this coming Thursday, not day after tomorrow Thursday, but the following Thursday, the 11th, is Honors and Awards Day. Now, that starts at 10 in the morning, and hopefully it'll be done before noon, okay? And if it is done before noon, I should be back here by 12:30, so hopefully class will start normally at 1:15. But that's a week from Thursday. We'll talk about that later. I don't think there's any reason for that to delay this class. But if you do have a 10 o'clock class and probably even an 11:30 class, it may influence those. Check with your instructors Thursday or next Tuesday to find out for sure. If you have an adjunct instructor, it may not affect your class at all. If you have a full-time instructor, we're expected to be over there. So, check. Now, mini-term classes, sometimes we can get out of going to those kind of events with mini-term classes. But, all right, so that's most of that. Now, here's another. I don't know if you've noticed various posters around the building with NCAS on them, usually in bright colors like that one. That stands for NASA Community College Aerospace Scholars Program, okay? And they will be beginning in the fall, 2019, but the applications are due, application deadline is May 15th, so you have just a little over 6 weeks to get the application in. They didn't send me an application, but they sent some website information. You can Google or search any way you want to for NCAS or NASA Community College Aerospace Scholars Program, and you can find out all the information you could possibly want to find out about it, probably including the application process and forms. We've had some students. In my last class, there was a student who had participated. He said it was great. I've heard other students be even more effusive than he was about it. Okay? And you learn a lot. I think you actually get to interact with actual NASA missions. You know, you actually get to participate in small ways, but with some of those missions. And so please check that out. I've got the information here if you want to get the website information from here, but you can find it multiple places. Okay. I think that's just about covers it. I think I got everybody here who is here. So any questions before we get going today? All right. Now, like I said, I think we did this slide last time, or at least the first part of it. Power is the rate at which work is done. Okay? The time rate of change of doing work or doing work, performing work, or using energy. That's what power is. The units are watts in the SI system, horsepower in the U.S. customary system. Today's lab will be walking versus running the stairs. And I don't have the material here. I usually get it first thing in the morning, and I was kind of tied up first thing this morning, so I didn't get it, but I'll get it right when we take a break from class here. Time out from here, too. Let's go over what today's schedule will be. We'll have class for the first 2 hours approximately. Part of that's already gone now. And then we'll have lab for 2 hours. And then we have the test on Chapter 2. Okay? So if you haven't gotten your material ready, the formula and equation sheet for Chapter 2, you can be doing that too. And you'll have plenty of time after lab. Lab is not going to take that long. We're not going to a specific room for the lab. If any room, it'll be this room. But what we're going to be doing in the lab is going to stairwells and walking and running the stairs. Okay, that's what today's lab is. You'll be timing, measuring, that kind of stuff as you do that. And then we'll come back here and do the calculations. So I don't think the lab will take the full 2 hours. You can certainly take it if you need to. And that means you'll have plenty of time to work on formula and equation sheet between lab and test time, or if you're ready already, you can take your test early and then sayonara and enjoy the spring day, though it's a little on the cool side. Okay, so any questions about how today's going to go? All right, so that's today's lab. 2 hours class, 2 hours lab, 30 minutes for the test. So it probably won't take you 30 minutes. So let's get down. This is where we left off last time, the very bottom part of this slide, talking about the power bill. Do any of you pay this, or mom and dad pay it?
Did you say a test today?
Yeah, Chapter 2 test today. Okay, I didn't say it very loudly or very repeatedly, but only several times did I say so.
I was double checking.
Okay, all right. Chapter 2 test today.
Chapter 2 test.
Yeah. Yeah. And you'll have time after lab and before the test to get ready for that if you're not already. Okay. Now, my question was, do you pay the power bill, or did mom and dad or somebody else? Any of you pay a power? You pay a power bill. Okay. Are you paying for power?
No.
No. Power is the rate at which you're using energy. What are you paying for? No, watts is power. Say again? What are you actually paying for? Have you ever noticed on the bill what you're paying for?
How much you use?
The active is
How much of what are you using?
electricity.
Okay. Measure how? Electricity is
Volts.
charges, huh?
Volts.
No, volts is a... Okay, we'll get to that in the later chapter.
Usage.
Okay, usage. What are we actually paying for? The energy you use, the electrical energy you use. Okay? Okay? The actual electrical energy, not the power. We call it the power bill because it comes from Alabama Power Company, but no, it's an energy bill. Okay? But what is energy? Or what is power? The rate at which work is done or energy is used. So if you think about that, power, whoops, let me get my pen set up. Okay, power is equal to work or energy, okay, divided by time, the time difference, okay? So therefore, energy is power times time. Now, some of you said watts. Watts is a measure of power. Actually, a bigger measure would be a kilowatt. And if you actually look at your power bill, what you're paying for is so many kilowatt hours. That's power times time, that equals energy. So you're paying for kilowatt hours, which is an energy, not power. The energy that you're using is measured in kilowatt hours. Now, they could have used joules, I guess, but a joule is a very small amount of energy. So typically, if you were paying for joules, you would be paying for millions and millions of joules. And people would say, oh man, I'm using that much energy. And they would say, start cutting back like crazy. So they use kilowatt hours, which is a huge unit. So even though the number is reasonably large, it doesn't seem that big, okay? A joule is a very small unit, so the number of joules you use is literally millions of joules a month, okay? And they don't want to put that on the bill that you're using millions of joules. It just seems like you're using too much. So they charge you in kilowatt hours. That may be not why they're doing it, but yeah, it is. Never mind. Okay. So with that in mind, here it is. Example 3.3, top of page 68. All right, I'm going to erase what I have here just because we need more room to write, but that's what we'll be using. Okay, an electric lift can raise a 500 kilogram mass, so that's 500.0 kilograms. They just told you what that is. What is that? Not weight. Mass. That's the mass. Weight is measured in newtons or pounds. Okay? A distance of 10.0 meters. That's pretty high. 10.0 meters. Now, you can call that either, they use the symbol, which I like to use, is H. That's your height that you lifted it. Okay? In 5 seconds. 5.0 seconds. That, of course, is, what's that a measure of? Time. Perfect. Okay. Now, what is the power of the lift? So we're now looking for the power. Okay? And here's Kelvin. Okay. Anyone else come in since the call roll? I think I got everybody. Okay? So, how do we get power from the information we've got? What?
Time. Wait, energy divided by time.
Energy divided by time. You're absolutely right. Energy or work, either one, divided by time, just like we had before. Okay, what is the energy or work done in this problem? Mass, that certainly is involved. Mass times what?
Mass times.
Okay.
Hours.
Yeah.
The H.
Yeah, so, yeah. All right. It's your first day here in this class, right?
Yeah.
Okay. before you get too settled, I've been carrying these around ever since the beginning of the term. These are just papers from last term. Okay. Now, there's a lot of stuff already happened. We're on the third chapter. First chapter had 1 lab. Second chapter had 3 labs, so that's 4 labs. The third chapter, we're going to have the first lab today. That's the 5th lab. So we've had 2 tests and 4 labs we're having the second test today. And so the first test and 4 labs we've already done. Okay. All right. So you'll need to get with me and get copies of those things and get with somebody else and get the data so you can fill those out. And you can listen to YouTube and get some of it, but not all of it, but you can get some stuff from it. Okay, now what we were talking about. Power is energy or work divided by time. We've got the time. What is your energy or work? And you said it had something to do with mass. What does that have to do with mass?
500.
Okay, that's the mass, but what does that have to do with either work or energy? Okay, and here we have Brandis, right? All right. We're doing example 3.3 on page 68. Okay, if you got your text. Okay. How do we get energy or work from what we have given, mass and height? We've already got time accounted for.
You can multiply the A to the M
Really?
to get your energy.
Okay, so that would give you kilogram meters. And that's the measure of what?
That's your Is it work?
Is that work? Is that what you said?
I don't know.
Okay. What is work? Does anyone remember what work is? Is the equation or formula? Work. Distance is involved with it, I'll give you that. But what is multiplied by a distance to give you work? It was, second? Force, exactly. Work is equal to a force times the displacement. In our case, that would be your H. Well, what's your force that we're dealing with here? We have the mass, but we don't have the force. There's Rhodesia. Okay. Oh, we don't have any force? Well, then I'd say we don't have any work. Now, what's the force you're dealing with here? If you're lifting a 500 kilogram mass, 10 meters, you've got some force. You better have, or else it's not going to go anywhere. What is the force? What are some different manifestations of force? Yesterday morning, after the stepped on them to see how bad spring break was for them. They kept going up, up, up.
No, that's not no good hit.
Not a good hint.
No.
Okay. What work am I doing when I lift this chair? What's the force I'm having to exert?
Gravity.
Okay, gravity is certainly involved with it. That's what I'm working against, okay? So, how do you get force out of mass and gravity? Oh boy. I thought that would give it away. That is the force. What I'm having to work against when I lifted the chair, I was lifting the weight of the chair. And weight is mass times acceleration due to gravity. So the force here is mass times acceleration due to gravity. That will be on today's test, okay, in many different forms and places, okay. That is what weight is mass times acceleration due to gravity. Force is mass times acceleration, F equal ma. The A here is your acceleration due to gravity. Okay? Now we have enough. Now we have enough to figure what this is. Work is force times distance, or height, but force is mass times acceleration, so this is mass times acceleration due to gravity times the height divided by the time. That's what power is. Work divided by time. Work is force times displacement. Force is your weight times the displacement is the height. Okay?
Where do you get G from?
What's that?
Where do you get G?
Where do we get G from? Okay, H we were given right here. There's the mass. Now the question is, where is G? What is G? What is G? Acceleration due to gravity. Let's assume we're on the surface of the Earth. Is that a fair assumption? Okay. What is G on the surface of the Earth? 9.8 what? Meters per second squared. And acceleration due to gravity anywhere on the surface of the Earth, that's it. If you're in the U.S. customary systems, it's 32 feet per second squared. We're in SI units here, so it's 9.8 meters per second squared. A constant anywhere on the surface of the Earth. Okay? So we have 500.0 kilograms times G, 9.8 meters per second squared, times a height, 10.0 meters, divided by the time, which is 5 seconds. Okay? What do we get? Anyone got a calculator? That'd be 5,000 times 9.8, which would be 49,000, I think, divided by 5. Pretty big number. Let's do it this way. Let's do the 5 and the 10 will be 2. Be 1,000 times 9.8 is 9,800. I think, yeah, 98,000. 98,000 what? Say again? We're measuring power, and what do we measure power in? We started that earlier. Watts, 98,000 watts. Now, if you wanted to use a smaller number but a bigger unit, what would that be? 98 kilowatts. Perfect. Okay. Let's see if that's what they got. Yes. Okay. But for some reason, and they didn't tell us why, they said they want this in how many horsepower is that? Okay? Well, you have to go back in the text for a little ways, and if you go to the previous page, you'll see that it takes 746 watts to equal 1 horsepower. So that would be 0.746 kilowatts for 1 horsepower. So this is kilowatts times blank blank equal blank horsepower. Now always put the units in the place. So what unit goes where on that second blank there? What unit goes where? One goes above, one goes below.
H.
Say again?
H.
8. Where do you get 8? I said a unit. Either kilowatts or horsepower. One unit goes above the line, one goes below. Which goes where? Always put the units in their place.
Kilowatts at the bottom.
Kilowatts on the bottom. Horsepower on top. And I just told you from the previous page, 0.746 watts, kilowatts, 0.746 kilowatts is 1 horsepower. So you take your 98 kilowatts divided by 0.746. And what do you get? No. Y'all told me wrong. I thought I had it right. Okay. 5 will go into 10 twice. 2 times 500 is 1,000. This is 9,800 watts, not 98,000. 9,800 watts. I was going to say that's way too much. Okay. So that's 9,800 watts. And how many kilowatts is that? 9.8 kilowatts. So do 9.8 divided by 0.746. Notice the kilowatts go away, and you're left with horsepower. 9.8 divided by 0.746. Almost 3/4. Anyone do it? Okay, and they just round the 13. The reason they round the 13, this is only 2 significant digits, that's only 2 significant digits, so we're going to leave it at 2. 13 horsepower, approximately. That's a pretty reasonable lift there. Okay? Now, let's do example 3.4. Everybody got this one? Can I erase it? Okay. All right. 3.4. A 150-pound person. What's that a measure of? 150 pounds. What's that a measure of? No, it isn't.
Pounds.
That is pounds. What is the measure of? Huh?
Ounces.
Okay, ounces is also a unit of weight. Huh?
Weight.
Weight, that's weight, and weight is also a what? Force, exactly. That's our force here, which is our weight. Weight is little w, so don't get that confused with capital W, watts. Okay? In 10 seconds. So 10.0 seconds is a measure of time. Okay? There's your time. What is the horsepower rating of that person? Okay? How do we get horsepower? Horsepower, by the way, is a measure of power. And what is power again?
Energy.
Say again? Oh, I left off something here. I misread it. A 150-pound person runs up a 15-foot stairwell. So 15 feet, that is your height that is going up. Okay. So, what is power again? Energy or work divided by time. And in this case, it's probably going to be work, though that's a form of energy. What is work?
Force times height.
Force times height divided by time. And do we have our force?
Yes.
Yes, what is it?
150.
150 pounds times the height. 15 what? Feet divided by 10.0 seconds. Okay? So that will be, I think, 150 is, say again? 2250, isn't it?
Yes.
That would be foot pounds. That's a measure of work in the U.S. customary system, divided by 10.0 seconds, and that would be your 225 foot-pounds per second. But they're asking for what's the horsepower. Does anyone recall the conversion between foot-pounds per second and horsepower? And again, you can look back that on page 66. Say again.
Horsepower divided by the weight.
Okay. Okay, wait a minute. Okay. You're trying to get to horsepower. Okay. So we're going to put horsepower on top divided by foot-pounds per second. The power there. But I need a conversion. how many horsepower are in 1 foot-pound per second, or how many feet-pound per second are in 1 horsepower. And that's what's on that page 66, same place we got the other conversion factor. And it says right there that, it's also in the picture on page 67 as well, but it says that the English units of foot-pounds per second to horsepower divide the power rating by 550 foot-pounds per second per horsepower. So it's 550 foot-pounds per second is 1 horsepower. So 225 divided by 550. And notice the foot-pounds per second, so all those big old units disappear. You're left with horsepower. What would that be? Anybody? 225 divided by 550. 0.4. We probably could use 0.41. Okay, about 0.41 horsepower. Let's see what the book got. 0.41 horsepower. Good for them. Okay. We'll see how that compares with your horsepower rating in lab today, right? Okay. Huh? All right. Okay. Now, I thought in all that they were going to go over the electrical, but they haven't yet. They will at some point. Don't know why they haven't yet. I say they will, but I don't see where they do. But I know you'll need to be doing those later. And I do not see. Maybe it's in the yeah, it's probably in the chapter on electrical energy. That's where we'll be doing it. I knew it's going to show up somewhere, but it's that chapter, not this chapter. Okay. So this is how we calculate our power. Okay? Now they have the picture of the guy. We saw this one before, walking up the stairs and going more briskly up the stairs. Who's doing the most work?
The man on top. The man on top.
Nope. Doing the same work. Same man, same height, same mass, same weight, same everything, same work. What's the difference in this though? Yes, and why? Because the time, it takes him less time than it does that old guy, the same guy, okay? But less time means more power. It takes him more power to get up the stairs than this guy who's up the stairs. Okay. So, we'll pick up on the power bill in a later chapter. Okay. Any questions on power? That's today's lab, by the way, right there. Walking and running up the stairs.
One person from each group?
What's that?
One person from each group?
Oh, no.
Everybody?
It depends on how much you want to ensure you get a good grade. But it's got to be at least 2 people per group. You can do more if you want to. What's that? Okay. All right. So that was power. Let's now move to motion, position, and energy. Okay? Now, they really don't sound like they have much in common, but the common thing here is energy. When something's in motion, it has one type of energy. We call that kinetic energy. When it has changing position, that's another kind of energy. We call that potential energy. Okay? So, let me make sure. Yeah, I got it. Okay. So, Work and energy are related to each other. Very definitely related. Here's a couple definitions. Energy is the ability to do work. Okay? If you have energy, lots of energy, you can do work. Okay? On the other hand, work is the process of changing the energy level. If I'm doing work on the chair, I'm basically lifting the chair. I'm changing its energy level. It had less energy when it's down there than when it's up here. And less energy here than if I put it up here. If you don't believe me, let me borrow your foot a minute and I'll drop it from here or I'll drop it from up there and you see which does more work on your foot. Okay? So work is the process of changing an energy level. Energy is the ability to do work. They're the same thing, just different sides of the same coin, you might say. Okay? Next. Why did they put a slide with next on it? Okay? There's a relationship between work and energy associated with position. That's the position part. Energy is involved in all this, but now we're going to focus on the position part. The relationship between work and energy associated with the position, and then we'll do work associated with the energy of motion. That's where the motion comes into play. I've already given you those two names, but we'll get to them later as well. So let's first do the position one. That's potential energy. The energy associated with position. Okay? Now, there's several types of potential energy. We're going to be dealing mostly with gravitational potential energy. Now, this right here that we're going to start now, this will be the lab on Thursday. Okay? So, stand by for it. Gravitational potential energy. Now, what you need to know, because gravity is involved, that means you're working against gravity. You're lifting something. So the important, one of the key measurements is how high, what height change you've had. Like I said, if I lift the chair this far, I've done a certain amount of work. I have to do more work to get it that far, right? Okay. Now, here to there, I really haven't done that much more work on the chair. It's got the same energy level it was back there. Here it's done, gravity has done work on me by pulling it down. So the change of height, just like we'll be doing in today's lab, that's the key here. And what we need is a reference height. Okay? So let's say I'm not going to lift the chair anymore. Let's say I'm lifting this book. That's much easier to lift. Okay? Now if I lift it up here, the height of interest is how high I lifted it off the desk. That would be its gravitational potential energy relative to the desktop. That would be the reference height, the desktop. But if I moved over here, same height here, but now I'm relative to the floor. So now it has a greater potential energy above the floor because it's higher than the floor. If I go over and hang it out the window, now there's a greater. Its reference height would be the ground down there. Or it could be sea level, which is even further down than that. So you have to designate what your reference height is, what you're measuring with reference to. Now, there's other types of energy of position. One is elastic, which we call spring potential energy. Okay, if you've ever worked much with springs, you know a spring is going to be at some sort of rest position if it's just hanging there. Okay, if you push up on it, it's pushing back on you, right? If you push up on it as a reference level, it's not pushing it back on you. But if you compress the spring, it's pushing back on you. If you stretch the spring, it's pulling up on you, right? So it's going to work relative to its position, okay? That's called elastic or spring potential energy. We're going to do a little bit of that, but not too much. In 2 chapters from now, we're going to talk about electrical potential energy. And for the person who said volts, that's what you're dealing with electrical potential energy, voltage, okay? There's a little bit more involved, but that's what you're dealing with. Work can change potential energy. Just like I just demonstrated. I do work on the book, I change its gravitational potential energy. I do work on a spring, I change its spring potential energy. I separate charges further apart or add more charges, stuff like that, I change electrical potential energy. We have all kinds of potential energies. In those little green leaves out there, there is, and in plants in general, there is chemical potential energy, because I can take the wood from that tree and burn it and produce heat. Well, I'm changing the potential energy, chemical potential energy, or of gasoline or fuel oil or diesel oil or anything else, and releasing that and making it into heat or motion or whatever I want. So there's all kinds of potential energy, okay? And work can change the potential energy. Now, kinetic energy, here they haven't told us what kinetic energy is yet, but kinetic energy can change into potential energy, okay? Now, I throw a baseball up into the air, okay? I give that motion, right? When I throw it, it gets a velocity, okay? That velocity is enough to change the potential energy of the baseball. But every bit of potential energy it gains, it's losing that much kinetic energy in motion because it's slowing down. Because as soon as it leaves my hand, that's the fastest it's going to go until it reaches the top, when it's going to zero. And then when it starts falling back down, now gravity is doing work on the ball, pulling it back down. So kinetic energy can change into potential energy. Throwing a ball into the air is just one example. Okay. Now here we have, let's not do this, but take a book, hold it out of the window of a 4-story building, okay? That book has potential energy. If you're just holding it above the floor in a 4-story building, that would be potential energy relative to that reference level, the floor. But if you hold it out of the window, then that would be from the ground, okay? It just depends on where you put your reference position. If you put it here, the book has positive potential energy here. If it fell all the way to the ground, but that was your reference level, now it has negative potential energy. It's going to take work to get it back up to the zero level, okay? So that would be negative potential energy. Most of the time, we'll choose the reference level to be as low as it can go in that particular problem, okay? If it's only going to go to the floor on the 4th floor, yeah, use that as a reference level. But if it could potentially go to ground, then we'll use that as your potential. You do the same thing in electricity. You choose your ground, okay? Not this ground, but ground, and that's what you measure your voltage from. You assume that's at zero, okay? So kinetic energy can change into potential energy. You drop the book, it's going to start picking up kinetic energy as it loses its potential energy, as the H gets smaller and smaller. So now it's doing the reverse of that. Potential energy is changing into kinetic. All right, so what is kinetic energy? That's the energy associated with motion. Now, it seems like we would have had, and we did. So let me back up before we get to kinetic energy and do a couple of examples with this one. All right. Now, shame on them. They didn't give us the equation in the slideshow. So I'm going to give you the equation. This is equation 3.3, and this is potential energy. And in my mind, it's gravitational potential energy. Because like we just said, you have all these different potential energies. Spring potential energy, gravitational potential energy, electrical potential energy, chemical potential energy, all these different kinds of potential energy. This one's gravitational potential energy. That is mgh. Now that should look familiar, shouldn't it? When we had the book or the lifting something up into the air, that's exactly the formula we used. That was the work you did to get it from the ground to 10 meters in the air. That's the gravitational potential energy you gave it. The amount of work you did was increasing the potential energy. Same formulas, okay? So, there's your gravitational potential energy, mgh. So with that in mind, what is the potential energy, specifically gravitational potential energy, of a 2.14, kilogram book What is that a measure of? That's your mass measurement, okay? That is on a bookshelf 1 meter from the floor. What's that a measure of? Height. Okay, very good. Okay, what is the potential energy? What is your GPE? Right there. Huh? Okay, 2.14, that's the mass, 2.14 kilograms times. Okay, you certainly have the 1.0 in there. Aha, you got your 9.8 what? Meters per second squared, and acceleration, and the 1.0 is your meter. That's your height, mgh. So that gives you, someone with a calculator going to have to do that one for me, something a little bit less than 20, huh? A little bit less than 21, or around 21.
20.
Huh?
It's 20. 20.
20 on the nose?
Yeah.
All right. 20, what units? Okay, kilogram meter per second squared, that's a Newton. But then when you multiply that by meter, a Newton meter is a oh, it's been a long spring break, hasn't it? Newton meter is a? No, Newton is a force. Newton meter is energy. What do you measure energy in? Say again?
Watts.
No, that's power. Some of these are, say again? No, horsepower is power. Okay?
No. Joule.
Ah, okay, perfect. 20 joules. Okay? Now, is that on the nose? They say here it's 21 joules.
Yeah, I didn't round it off.
Okay, well, we had two significant digits everywhere. Okay, well, that rounds to 21.
Yeah.
21 joules. Okay. Now, I was going to ask this dumb question earlier, but I think I'll do it now. This has nothing to do with physical science. It's just a dumb. What's the past tense of spring break?
Take a break from everything.
For me, it was spring broke, because we did our taxes over spring break. And it confirmed something I had suspected and really known in the heart of hearts for a long time. I'm not among the wealthy. Because the tax cut that we were supposed to have had this year was for the wealthy. And I found out I didn't qualify, because our taxes, my wife and I, we usually don't have too much held out, so we pay a little bit of tax. That's what we want to do. We get to use our own money through the year, and we have to pay them a little more at tax time. Usually it's between $1,000 and $2,000, somewhere right in there. Okay? This year, between $8,000 and $9,000. So this was a great tax break. It was a wonderful tax break. And we actually paid estimated taxes on top of what they were pulling out, and we still had to pay that. So I'm spring broke. Okay, never mind. Not quite. I married money, so I'm not worried about it. But anyway, we were talking about joules. Okay. So anyway, 21 joules. All right. Now, let's do example 3.6. And that says, how much work can a 5 kilogram mass, 5.00 kilogram, what's that a measure of? Mass, do if it is 5 meters above the ground, 5.00 meters above the ground, what would that be? The height, okay. All right, how much work could it do? What's the formula for work? Or change of energy?
Power.
No, power is something different. Huh?
H.
mgh. Perfect. And what's your M? 5.00 kilograms times 9.8 meters per second squared times 5.00 meters, and that will give you something a little bit less than 250, right? 245? What? Joules. Perfect. Now, even though these have 3 significant digits, the 9.8 still is only 2, so I'm going to guess the book is going to say about 250 joules. Is that what they say? Yes. Okay. 250 joules. I would accept 245 because some books actually use 9.80 to 3 significant digits, so that would be fine too. Okay? All right. Any questions on that? That's gravitational potential energy. Okay? Now, the little concepts applied there on page 69, that's exactly our lab today. We've shown it in the pictures. Now they have it in concepts applied. That's what we're doing in lab today. Okay? So, let's move on to kinetic energy. This is where we started to go. Kinetic energy. Kinetic means moving. There is a whole field of study called kinesiology. I had a nephew, my wife's nephew, who did his undergraduate degree in kinesiology so he could go on and do physical therapy for his doctoral degree. Okay? And he is a physical therapist now. So it's the energy of motion. Kinetic, moving. Energy associated with motion. Now what, from chapter 2, what was the parameter that indicated something was in motion? Something's in motion, it has to have a what? Okay, it doesn't have to have an acceleration. Say again?
Speed.
Yes, speed or velocity. So energy that dealing with anything that has velocity or speed. Now that can result from work. Okay? Say that this is just an imaginary problem because I probably couldn't do it. If someone threw a baseball to me and I was holding a bat and I swung and actually hit the ball, which that would be the imaginary part, and actually hit the ball, I would then be doing work on the ball, changing its motion. It was coming at me, now it's going by. No, it's going out wherever it's going. Okay? Any kind of work that changes the potential energy. Or it could be this. Or a change of potential energy. If I drop the book, dropping it means initially what was its velocity? 0. And as it falls, it's gaining velocity, so the change of potential energy is also resulting in kinetic energy. Now, they don't give you the formula. I will give you the formula. I don't know why they wouldn't put it on the slide set, but here they didn't. Here's the formula for kinetic. Well, maybe they do. Let's just see. Yes, they do. Here it is. Kinetic energy is 1/2 mass times speed or velocity squared. Okay? You double the velocity, 4 times the kinetic energy. 4 times. Triple the velocity, 9 times the kinetic energy. Okay? So it depends on the velocity squared. Now, I think I mentioned to you before, many times in physics, if your parameter is squared, you're going to have a 2 in the denominator in front of it. Just about every time. The one exception was your centripetal motion was just mv squared over r. No. Yeah. mv squared over r. That would be centripetal force. V squared over r would be acceleration. There you didn't have a 2, but almost all the rest of them you'll have a 2 in front. Okay? Now, what does that mean for you in a practical sense? When you're driving down the expressway, say in town you're driving at 30 miles per hour, right? Okay? you don't have to leave so much distance from you. You need some distance between you and the car in front of you. But if you're on the expressway at 60 miles per hour, okay, let's take it back. Let's say a highway out in the country at 60 miles per hour, you'd better leave twice as much distance, 4 times as much distance between you and the car in front of you. If you're on the expressway at 90 miles per hour, number one, you're probably going to get a ticket, but number two, you better leave 9 times the distance between you and what you had to leave when you're at 30 miles per hour in town. It makes a big difference. Maybe I should have used 20, 40, 80. Okay, that would have been better probably. Or 60 or something. Okay. So, when you double the speed, your kinetic energy increases by 4 times, and therefore your stopping distance increases by 4 times. Okay? Don't know if we'll have an example of that, but it's something that's pretty important. So tailgating on the expressway, not a good idea at all. That's where these multi-car pileups come from. Nobody has a chance to stop when one thing happens weirdly. Okay. Wow. So let's back off and do a couple of examples with, let's go back to this one. Oops. Okay. Earlier we said potential energy, specifically gravitational potential energy. What was that formula again? mgh. Okay. And the units there were, mass was kilogram, acceleration was meters per second squared, and height was meters. Okay? So that comes up to be kilogram meter squared per second squared. That is a joule. Right? Okay, kilogram meter per second, that was a Newton. Kilogram meter squared per second squared, that's a joule. Well, let's see what the units are here. 1/2 doesn't have a unit. Mass has a unit of, what's the unit for mass?
Kilogram.
Kilogram. And velocity is? Meters per second. But then you square it, you get kilograms meter per second squared, and guess what that is?
4 times.
That's a joule.
Oh, that's a joule.
Yeah, kilogram meter squared per second squared is a joule up there. It's a joule down here. So both potential energy, kinetic energy, and work are all measured in joules. Kilogram meter squared per second squared. Or foot-pounds would be the U.S. equivalent of that. It doesn't have its own name. Okay. So, wanted to hit that before we got to the problems. Okay? Okay. Let's do example 3.7. A 7.00 kilogram bowling ball. What's that a measure of? That's the mass of the bowling ball. Is moving in a bowling lane with a velocity of 5 meters per second. So 5.00 meters per second. That's what? It told you. V, velocity, or speed, okay? What is the kinetic energy of the bowling ball? KE is what? 1/2 times M times V squared. Got it. So that'd be 1/2 times, and what's the mass? 7.00 kilograms times 5.00 meters per second, but you square that. Velocity squared. Be 1/2. I'm going to write that 1/2 as 0.5. Is that okay? Because it's going to be easier. Times 7.00 kilograms. And what's 5 squared? 25.0 technically. But you square your units as well, so they'll be meters squared per second squared. Okay? And this will be, pull out your calculator, 7 times 25 will be,
87.5.
okay, the whole thing is 87.5? 87.5, and that would be what unit? Joules. Very good. And they left it as 87.5 because everything had 3 significant digits. Now you might say, wait a minute, the 1/2 did. Yes, it did. You could have written that as 0.50000000 because 1/2 is a pure number. It can have as great a precision as you want it to have. Okay. So yeah, 87.5 joules. Very good. Let's do 3.8. All right, for me to erase? Okay. 100-kilogram football player. That's a measure of what? That's the mass of the football player. Okay. Okay. Is moving with a velocity of 6.0 meters per second. That was what? Velocity, V. Tackles a stationary quarterback. It means the quarterback is at rest. He just has released the pass and he's not moving. This linebacker is coming in here with a significant kinetic energy. Okay? The quarterback has no kinetic energy. Think he's going to do some work on the quarterback. What kind of work will he do? He's going to change that kinetic energy into work. Okay? Because at the end, the quarterback and the linebacker are going to be on the ground. The quarterback not feeling too good. The linebacker pretty happy with himself. Okay? So how much work did he do? Say again?
300.
How'd you get that?
I multiply half weight.
Okay, the kinetic energy of that football player, that linebacker, is 100, is 1/2 of 100 kilograms times 6.0 meters per second squared. So that would be 1/2. I'm going to do 1/2 of 100 is 50. 50 kilograms times, and what's 6 squared? 36. Square the units as well. Meter squared per second squared. And 50 times 36 is 1800. Okay. 1800 what units? Joules. If you want a little bit smaller number but a bigger unit, what would that be? 1.8 what? Kilojoules. Joules. Kilojoules. Keep the unit. Yeah, kilojoules. 1.8 kilojoules. 1800 joules. Quarterback will feel that the next day. He's probably feeling it at the time, but he'll feel it even more the next day. Okay. So there's kinetic energy. Gravitational potential energy and kinetic energy. Okay? Let's move on to, now y'all keep up with me. We go until 3:15. So we've got, what is it now? About 2:30? No, yeah. Right, 2:30, yeah. Okay. So got about 45 more minutes. Okay. So now let's talk about energy flow. Now that's sort of a weird kind of a statement if you think about it too hard. They act as if energy is a fluid and flowing. And actually in the earliest days, people really thought energy was some sort of ephemeral fluid that was contained in things, like wood. You strike a match to it and it burns and the wood goes away and it gives off heat. So they thought the heat or the energy was some type of fluid that was somehow contained in the wood. We know that's not true now. But that led to the concept of energy flowing. So we talk about energy flow, even though energy is not a material like a liquid that can flow. But we still use that. And here's what we mean by that. Energy can do work as work against. That's sort of a weird way to say this. Work against inertia. Okay? What does that mean? Okay? What are two forms that inertia can take on? Being at rest. So if I'm going to move the desk, I'm going to have to do work on the desk to get it to move, right? Okay? That's work against inertia. Or, if I decide to throw Brett a bowling ball as hard as I could, he's going to have to do work against that inertia of motion to get it not to hit him or to stop, right? So that's work against inertia. Changing its speed, changing its direction, changing anything about it, that's inertia, okay? Work against gravity. That's what I was doing when I lifted the chair or the book. I'm working against gravity, lifting something while the gravity of the earth is pulling it down, okay? Work against friction, okay? I don't know if you noticed that when I first tried to move the desk, it was sort of stuck to the floor. I really had to give it a shot to do it because, as you hear that, there's friction against the floor, okay? That's more of the work I'm doing than actually the weight of the desk, working against friction. Work against shape. Okay, now they have some of these. Let me show you pictures of this. This is work against inertia. If you've ever tried to push off a car, trying to jump start a car, you know you're working against the inertia of that car trying to be at rest. Now, how you do that is get it rocking. You've done that before too, haven't you? You're using the resonance of the car to your advantage. But if you're just trying to brute force move it, you better be doing it on a little Volkswagen Beetle or something like that, because you're not going to do a big heavy one very well like that. The inertia of the car is trying to keep it in place. You're trying to change that inertia. And the amount of force you move, and if you are able to move it any time or distance, that's the work you're doing. If you're not able to move it, you're doing no work, even though you're exerting a lot of force. So that's work against inertia. Work against gravity, as I just said, was lifting something. Lifting the book, lifting the box, lifting the chair, whatever. Here, the force that you're existing is the weight of the box. That's the force you're having to do to lift it. If you don't supply enough force to overcome the weight, you're not going to move it, okay? But if you do exert that much force and move it a distance, that's the work you've done against gravity, because gravity's pulling it down, okay? Am I doing any work by letting the book fall? Nah. I've already done the work to get the book up there. Gravity is now doing work to make it fall. Okay, work against friction. That's pushing something across the floor like this desk or something like that, and the friction between the floor and the box, that is what you're working against, and that is your force. If you are able to move it a distance, the force you're pushing this way works against the friction, which is trying to keep it in place. That is your amount of work you're doing against friction. Now, before we do the one against shape, I want to give you my example of work against shape. When I was in college, including grad school, I liked to participate in intramural sport activity. I just liked to be doing something. I just needed to release, to get out and blow off some energy, okay? And I played intramural football when I was an undergraduate, intramural basketball, and when they were fluid, I enjoyed playing intramural volleyball as well. And there was this one time we were on a group of us got together, an intramural volleyball team, and it was co-ed. That made it fun too. And we were playing against, this team, and we were in the gym and, knocking the volleyball around, getting warmed up and stuff. And we looked over and saw this team that we're going to be playing. They had this gal, you could tell, she had played some volleyball. She was tall, she could jump, long old arms, and we were watching. She had this buddy who could set it perfectly. I mean perfectly for her. And we thought, oh boy. We had a tall gal too who knew how to spike, and we had a really good setter. But boy, that was like we were amateurs, they were the professionals. I mean, you could tell they knew what they were doing. Okay? And if you've ever played volleyball, you know that your team rotates around one way, the other team rotates around this way too. So at some point, you're going to wind up across the net from everybody else on the other team. Somehow, sometime. Okay? And when it came time, sure enough, there I was, and this gal, the spiker, was on the other side. And we served, or whatever it was, and I saw her setter get under it perfectly and put it up there, right across the net from me. So I went up as big a block as I could, went up in the air. Oh, and if you've ever played volleyball, now it's not as hard as a baseball, obviously, but that volleyball is not soft. It is pumped up really tight, okay? So it's not a soft ball at all, okay? And I went up as much as I could go up, make as big a blocking target as I could, because I knew it was coming. And she came down with a spike. My hands did no good up there, hit me dead in the face. And I felt the ball touch each ear at the same time. I did some work against that volleyball, or that volleyball did work against my face. That's what it felt like it was doing. But I changed the shape of that volleyball big time. Okay, and it fell on my side of the net to boot, so it was a wasted point as well. So anyway, there's work against shape. A little bit better example, perhaps, was this one. When you stretch a spring or compress a spring, you're working against the natural equilibrium position of that spring. You're either stretching it and it's pulling back, you're compressing it and it's pushing against. They show you're doing work against the spring. The shape, the original spring was out here, you're compressing it this way. The force times the displacement, that's the work you're doing against the shape of the spring, or volleyball, or whatever it happens to be. And any combination of the above. Okay? So those are all ways that energy is changing things. Changes the inertia of an object, changes the gravitational position of the object, moves against the friction of the object, against the shape of an object, or against a combination of those. And actually, if you've ever seen it, have you ever seen a slow motion shot, and you can pick your object, a bat hitting a ball, a club hitting a golf ball, or a tennis racket hitting a tennis ball. If you've ever seen a stop action shot of that, and it's hard to believe, as hard as a baseball is, if you see a picture of someone taking a big swing at that baseball and hitting it, that baseball actually deforms. The bat deforms the ball, and the ball sort of wraps around the bat in many ways and then springs back off. It resumes its regular shape. That's the elasticity of the ball. It resumes that shape. And a tennis ball, if you see that tennis racket bulges back and that ball flattens out against it and then goes. When Serena Williams hits that tennis ball, I tell you, there is some flattening of the ball and some bending of those net strings because she is walloping that ball. Okay? Same thing with a golf ball. As hard as a little golf ball is, when you see the slow motion shot of that ball actually flattens against that golf head, flattens, not completely, but flattens against it, and then springs off, resuming its shape. It's amazing to watch. If you can ever see that, look at it. You can probably find that on YouTube or some sort of video somewhere. All right, so let's move on from energy flow to energy forms. Okay? The working energy, that's what these were. We just talked about those. So energy forms on page 71. Okay? Now here's a new one. We haven't mentioned this before, but it's a combination of other energies we have talked about. Mechanical energy. Get this. We'll be using this not in today's lab, but in Thursday's lab. Okay? Mechanical energy is the sum of kinetic energy plus plus potential energy. It doesn't have to be gravitational potential, though the one we do will be. But it's the sum. Mechanical energy is the sum of gravitational plus potential plus kinetic energy. Okay? In 2 chapters from now, we'll be talking about electrical energy. We'll be talking about charges, currents, voltages, those kinds of things. Okay? We'll get there later. We'll come to that later. Chemical energy. The energy involved in chemical reactions. Those little green leaves out there are right now converting energy. What they're doing, they're getting the energy from the sun, electromagnetic radiation from the sun, light, in a process called photosynthesis. Photo meaning light, synthesis meaning creating something, making something, synthesizing something. What are they synthesizing? Well, they're taking carbon dioxide from the air. The leaves have little, they call them, you might call them pores. They're like our skin pores, but they're small holes. They actually call them stomata. Okay, that's the name they give for leaves. And they intake carbon dioxide. They get water from the roots, from the soil, and they combine the carbon dioxide plus the water. I'll actually give you that chemical reaction here. CO2, that's carbon dioxide, plus H2O, that's water, and somehow, using the photosynthesis, the chlorophyll that's in those plant leaves, they create sugars, C6H12O6. Now that could be fructose, glucose, or sucrose. All 3 of those have that same formula. They're just arranged a little bit differently. And that's what's going on there. Now, obviously, there's 6 carbons here, so you have to have 6 carbons here. There's 12 hydrogens here, so you have to have 12 hydrogens here. And there are 6 oxygens. Have I done this wrong?
I thought they were supposed to be up.
Say that again?
I thought they were supposed to be up, like, exponents.
No? Okay. I'm doing something squirrely here. I can't figure it out yet. This would be 12 and 6. That's 18 oxygens. Where are all? Plus. Yeah, that's where it is. There's oxygen given off. That's the other thing that those plants are doing. They're taking carbon dioxide out of the air and releasing oxygen into the air. And you guess what? If they weren't doing that, we're not here. Because we require oxygen to breathe. Oxygen just doesn't happen everywhere. Those plants are releasing every bit of the oxygen we're breathing. They've released it. Okay? So that's where the other 6. So you had 6 here, you have 18 here, so you have 6 here too. Now it's balanced. 6 carbons, 6 carbons. 12 and 6 are 18 oxygens. This is 6 and 12 is 18 oxygen. 12 hydrogen, 12 hydrogens. Yeah. That's what those plants are doing for us right now. Number 1, they're making the sugars that we are going to eat. Okay, that maple tree isn't making any maple sugar, but it's making sugars that it's using, like the wood is carbohydrate, which is a sugar process made more complicated, okay? But if that was a soybean plant, it's making sugars. If that's a fruit tree, it's making sugars. Whatever it is, strawberry vine is making sugars, okay? And we consume those, and we use the oxygen that it gives off. Thank you, plants, okay, for doing your jobs. That's chemical energy. Well, that's usually stored chemical energy, taking radiation energy from the sun, storing it in those chemical bonds. So you see, it's broken apart, these bonds, put these together. Later, when we eat the sugar, we metabolize and we're able to do work, okay? Because we have the energy to do so, okay? And we actually burn oxygen and make it into carbon dioxide and water vapor. So we just reverse that process when we do work, okay? Then we have radiant energy, okay? That's what I was calling electromagnetic energy that we get from the sun. Now, there's a whole bunch of electromagnetic energy out there. Tons of it. Visible light is the only small part in general that comes through our atmosphere. Thank you, atmosphere, because some of the high energy radiation out there, that gets blocked. If it came through, we're dead. We're dead meat, okay? Because gamma rays kill us. They kill tissue. X-rays kill tissue. Now, the X-rays you get in the dental office, but really low level and only small charge at a time, you overcome that. But if you receive the radiation that is outer space, you're dead meat. That's why those astronauts, when they're walking and doing the space thing up there, they got on the big, bulky suits. Part of that is to provide pressure. They got to have the pressure. The other part is silvered suits to block that radiation from coming in. If not, they're dead meat. Okay. Visible light, that little small part that comes through the atmosphere, that's it. Now, a little bit of ultraviolet light comes through too. Ultraviolet light damages tissue. Okay? I have right here a little red spot that's pre-basal cell cancer. Now, I've had it for many years. I put sunblock on it every day. Winter, spring, summer, and fall. Every day, if I'm going to be out in the sun, which every day I'm out in the sun a little bit, I have to have the sunblock, otherwise that becomes cancer. That's called ultraviolet radiation. I've had cataract removed from this eye about 9 years ago because ultraviolet radiation over time messed up my lens, so I couldn't see through it well. They took it out, put a new lens in there. And in June, I have this eye done because that one's now gotten bad enough I have to have that. That's done by that. All these other old age spots, ultraviolet radiation is causing those. Okay? That other stuff kills cells. Okay? Visible light does not. Okay? Nuclear energy. That's the energy involving the nucleus of an atom and nuclear reactions, which is splitting the atom or combining atoms, fusing atoms or fizzing atoms. You know, one or the other. Those are nuclear reactions. Enormous amounts of energy comes out of every one of those reactions. Hopefully we're controlling it. The atomic bombs, out of control. The nuclear power plants, controlled. The nuclear plants on submarines or aircraft carriers or other big ships, controlled. We hope they're controlled. Chernobyl wasn't controlled, out of control. 3 Mile Island, out of control. Fukushima, out of control. Okay? Very dangerous when that happens. All right. Those are your various energy forms. So energy is always being converted from one form to another form. Sorry. Any form of energy can be converted to another form. I wish that were really true. Low-level heat is hard to convert back to anything. So that's usually wasted energy. Okay? You can't really get a lot of good out of it. Energy flows from one form to another in natural processes. Okay? We're going to talk about this a little bit more later, but let's talk about it now in terms of a pendulum. This will be Thursday's lab. Okay? Let's talk about, okay, wait. First, let's got the guy with the bowling ball. We did an example earlier. Here we go. What kind of work is happening and energy transfer is happening with this bowling ball? Number one, it's pretty massive. If you've ever picked up a bowling ball, it's no small thing, okay? It has a fair amount of mass, right? And look what he's done with it. He's lifted it way up here. So in lifting it, he's giving it what kind of energy? Changing its position. Second? No, okay. Potential, because he's changing the height of it above the floor, okay, and lifting that up. Now, when he starts his movement down, he's letting the ball drop, changing its potential energy, but also he's putting some muscle power behind it, and he's giving it kinetic energy. So now that potential energy is changing into kinetic energy here. So he did work to increase the potential energy. He does a little more work to give it more kinetic energy. Now all the kinetic energy is got. It's not picking up anymore. Maybe losing a little because you can hear vibration with the floor, but not very much because they keep that really polished, nice flat level, so not a lot until it does work on those pins. My bowling balls do work in the gutter, okay, unfortunately, but these do work on the pins, okay. He knows what he's doing. And it gives the pins kinetic energy because they're just sitting there until the bowling ball hits and then they go all over the place. So he's giving, the bowling ball is losing some of its kinetic energy, giving the pins lots of kinetic energy, okay. It's doing work on the pin, making them move a distance, okay. Now, that's not a pendulum. That's bowling calls, okay. This is a pendulum. Now, this can be a string or it could be a solid rod here. Either way, that's a pendulum. You've probably seen these too, right? Where do you see these? As a clock? Is that what you said?
A park.
Oh, a park, yeah, okay. A swing is a pendulum in many ways, okay? Yeah, so anything like that. Have you ever seen a grandfather clock?
Yeah.
Yeah, that's a pendulum, okay? All those are pendulum, okay? Now, what you do with the pendulum, and this is what we'll be doing in lab on Thursday, we'll put a mass down there on the pendulum, which has weight, multiply the mass times acceleration due to gravity, and we'll lift that to here, okay? So we're increasing its potential energy. Okay, we'll hold it there, and then when we release it, it starts falling. As it starts falling, it's losing potential energy because it's changing its height, but it's also gaining kinetic energy until it has the maximum kinetic energy here. It can't go any lower than this because of the length of the string, so it's now all of its energy is kinetic energy. Up here it was all kinetic potential energy, gravitational potential energy specifically, with no kinetic energy up here if it's at rest, because zero velocity, zero kinetic energy. Somewhere down there it was 50%, about halfway down, 50% kinetic, 50% potential. Down here it's all kinetic, no potential because it's reached zero reference level. There's that reference level there. That's as low as it can go in this particular application. And then it comes on up and comes just about the same height over here. Okay? And then it stops. All of its energy is kinetic now, potential now, no more kinetic, and then it falls back down and starts reversing the process. Losing potential, gaining kinetic till it reaches its maximum kinetic down here again. Guess what energy is the same throughout that process? The sum of potential and kinetic. Mechanical energy. Mechanical energy is conserved. Okay. That's the pendulum. Energy flows from one form to another form all the time. Smoothly, consistently, changing from kinetic to potential to kinetic. Over and over and over. Okay. Now, the energy of the pendulum is basically fixed. It's constant. Whatever energy you give it here, once you release it, the energy doesn't change. It changes form, but the total energy remains the same. Mechanical energy remains the same. Kinetic is always changing, potential is always changing, but its total energy is constant. Mechanical energy equal kinetic plus potential. I'm going to go on and write that in this way too. Mechanical energy is equal to kinetic energy plus potential energy. Okay, makes sense? All right. Energy conservation. Okay? You might say, well, if energy is never created nor destroyed, who cares about conserving? Well, no, we're not conserving it. Energy is conserved. Okay? Now, we'll find there's a little exception to this later, but we'll just deal with this now. Okay? Energy is never created nor destroyed. It just keeps changing its form. Energy can be converted from one form to another, but the total energy remains constant. Okay? I think I used this in an example before. When you're hitting a pool shot, right? Originally, 15 balls in the rack? Yeah. 15 balls in the rack, they're at rest. Zero kinetic energy, zero potential energy, they're at rest. Okay? All the energy is given to that one cue ball when you hit it, right? All the energy is given that. If you give it enough when it hits that rack, then all those balls take off in all sorts of directions, but their total energy is exactly equal to the cue ball energy before it hit. Exactly equal, except for any they may have lost. Okay. Okay, total energy remains constant. Free fall. If I release an object from up here, what's its kinetic energy if I release it from rest? Zero, because it has no velocity. Initial velocity is zero. As soon as it leaves my hand, it starts losing potential energy, gaining kinetic energy. And it keeps doing it until it hits the ground. Okay? The energy transfer mechanisms, it either changes into work or it changes into heat, one or the other. Now, when it hits the ground and stops, it either dents the floor, which probably wouldn't, or it produces heat. And if you had a fine enough thermocouple down there, you would see the heat jump up ever so slightly. So those are the two transfer mechanisms. Okay? Try this. Rub your hands together. Pushing on them. Okay? They get hot, don't they?
Heat.
Because the kinetic energy is changing to heat energy. That's your transfer mechanism. Okay? Now, here's the formula. The potential energy you lost when you dropped the ball from rest is at its maximum potential energy there. The energy it lost as it went down is the amount of kinetic energy it gained. Potential energy lost equals kinetic energy gained. Well, potential energy lost is mg, and this really should be a delta t, delta h, how much distance it changed there, mgh. And the energy gain was 1/2 mv squared. At any point, this velocity is related this way. Well, guess what? The mass is the same on both of those. You can divide those out. And multiply both sides by 2. That gives you 2gh is equal to v squared. And then take the square root. There's your velocity at any point along the way. If you know how much it fell, the change of height here, that's why I said delta H, the change of height is related to the final speed. Every point along the way. We'll be doing that in the lab on Thursday as well. We can either use that formula or the one above, one or the other. Okay? Now, I'm not turning my pages fast enough here. Okay. Oh, let me go back a few slides. Okay. That radiant energy, I wish they had this in a slide. I don't know why they didn't. This is what I was talking about. I forgot that they had it in the book. For folks at home, you can't see it, but that's too bad. You should be here. Okay. Now, this, and by the way, you can open your books to page 73. You'll see what I'm talking about here. Here is the energy spectrum. This is all electromagnetic energy. The very highest energy rays, which are given off either in nuclear reactions, like a nuclear bomb, or those nuclear power plants, or a nuclear power plant on a submarine, or an aircraft carrier, or whatever, destroyer, not destroyers usually, cruisers and things like that. But especially those given off by the sun, that's the very high energy gamma rays. These, say again?
Like solar light.
Okay, no, solar light is giving off, visible light. Okay. But the gamma rays are really high energy. They will destroy tissue enough that in time will kill you. Okay? Do you remember the story? Oh, what was it? Probably maybe even 10 years ago, of the Russian spy that had turned and was living in England, and the other Russians got to him and mixed some radioactive material in his food. Killed him. Okay, and that was one miserable, painful death, because every place that radioactive material went in his gut, it started killing cells. So basically, he was dying from the inside out. And that was a slow, very miserable death. They're pretty corrupt people. Okay. That high energy radiation will, not immediately, but it will kill you. Okay. X-rays, they're not quite as serious, but they will. Then comes the ultraviolet. That's what causes wrinkling of skin. You know those sun worshippers in their youth? You know what you call them nowadays? Prunes. Because their skin is all wrinkled and because all that extra sun they got, it hurt the skin tissue. Okay? So, ultraviolet rays. Fortunately, our atmosphere blocks most of them, but a lot of them do get through, and that's why you get sunburns, that's why you get cataracts, skin cancers, that kind of stuff. Then this tiny little visible spectrum here, starting at the violet light up here just below ultraviolet, going down to your red just before the infrared here, that's all that this atmosphere lets through in good abundance. And that's all the plants need to make their chemical reactions. That's all we need, okay? But we get some ultraviolet as well. When it reaches here on Earth, then and interacts with things here, it loses a little energy, so its wavelength lengthens some, and it becomes infrared radiation. Well, infrared radiation is heat. Now, some heat escapes back into the atmosphere, but not that much, okay? Because it's easier to come in when it lengthens up some, lengthens the wavelength and loses energy, then the infrared is harder to go back out again. Now, I bet you, did most of you drive here today? Okay. I'm guessing you probably left your windows up, or did you crack them? You did crack them? Okay. Okay, if you didn't crack them, your car would have been pretty hot when you got in. Now, it was still in the 40s when I got here this morning, so I left my windows up. Now, if I were going to leave right about now, I'm not, okay? But if I were going to leave about now, oh, I'm certain of it, okay. My vehicle would be hot inside. I'm probably going to leave around 6 this evening. It will have cooled off enough. It'll still be warmer than outside. But why is that? Because the light rays from the sun, the electromagnetic radiation from the sun, and this tiny little spectrum here, when it passed through the glass, it lengthened it a little bit, and it became infrared heat energy. That's why the inside gets warm. But that heat can't get back through the glass, or most of it can. A little bit can, but not most of it. So that's why the entire interior of your car will heat up. And in the summertime, do not leave your pets, and certainly not your kids, in a closed-up car. You can kill them, okay? And it will not be a pleasant death either, okay? Because they get way, way, way too hot, okay? And that has happened at some daycares, that they take the kids on a field trip or something, some kid falls asleep way in the back of the van, they're not keeping good count, they close it up, they go in, play at the Splash Adventure or whatever, and come back out a couple of hours later, that kid may be seriously sick, okay, because the heat in the summertime, way too hot in that vehicle, okay. So, that's what the worry is about with, and by the way, people who work in horticulture, they, in fact, my wife and I and our dog too, go to, any ever heard of Pepper Place Market? Okay, we go every Saturday it's open that we're in town, okay? And our dog knows it too. She loves going there, okay? And the people, when it opens, I think it opens maybe this Saturday or next Saturday one, when it opens, a lot of those vegetables didn't grow in the garden. Where did they grow? Because it's just too cool. Yeah, in the farm, but where? It's too cool for the plants to produce those tomatoes right now. How did they grow those tomatoes? It wasn't outside, it was in a greenhouse. Okay. What the greenhouse does, same as your car windows. It lets the light come through electromagnetic radiation, but then it lengthens the wavelength and it doesn't have enough energy to go out, so the greenhouse heats up inside. Many of our plants that we keep on the patio and things like this, we keep, it's a real small greenhouse, but it's a greenhouse in our backyard, and except for nights like we had a few nights ago when it got down, they were afraid it was going to get in the upper 20s. I turn on a light inside there because it won't keep it that all night, but just keeps it warm enough. But in the daytime, nice and warm in there. I have the same plants been blooming all winter long in that greenhouse, okay? Little greenhouse, but it's a greenhouse. Well, that's what is happening with our atmosphere now, especially when we put extra amounts of carbon dioxide, which we have been doing since the Industrial Revolution. If you think about it, we'll talk about this in a later chapter, but those plants and plants before them, for hundreds of thousands to millions of years that there have been plants and things on this planet, all that leaf mulch and stuff like this in the bottom of the ocean, organic matter is just built up and piled up and piled up and piled up, and some of that changes into coal, and some of it changed into oil, petroleum. Okay, and it took hundreds of thousands to millions of years for all that to convert. Well, what we've been doing since the Industrial Revolution, which is, the 1870s or 80s when that started and really got going in the 1900s and stuff, we've been burning that stuff, the coals, the fuel oil, the gasoline, the petroleum, all those things, we've been burning them as fast as we can get them out of the ground. So we've been releasing carbon dioxide at much higher levels than is normal, okay? It's not incredibly high, but it's much higher than is normal, and that carbon dioxide acts as a greenhouse gas, preventing that heat from going back into the atmosphere. That's why we're having, now this is the theory, global warming happening. That's why there are some places, go down to some of the beaches in Florida, and you'll see businesses that used to be on the beach. Those buildings are evacuated now because water is in the first floor, because the ocean levels are rising. There are some island communities that are seeing their islands get smaller and smaller, just by little amounts, but every year. Glaciers are melting, the sea levels are rising because the earth is warming. Okay, I won't get into the politics of it, but it is happening, okay? But anyway, so energy is changing forms all the time. That's why I wanted to point out that picture. Below that in the energy level are your microwaves, your FM and television, and then your AM radios are down here, and then there's long radio waves below that. These are all things we're producing. That's electromagnetic radiation, but it's not harmful in many ways at all. Okay, so I did want to show that. Okay. Okay. Here's what I wanted to get to. Here's the formula we were just talking about a few minutes ago before I got back and did the other thing. So let's do, okay, before we do that, let's do this one. This is this figure 317 in your text, and it shows free fall. That's what we're talking about right here, example of free fall. If, okay, 10 meters, that would be about like a 3-story building. Okay, now this building is only 2 stories here, but the part just below us here, there's 3 levels. Okay, and if you went up on the top level there, the 3rd floor where they have the business classes, the accounting classes, those kind of classes, that's 3 levels up. That would be about 10 meters from the ground outside those windows. So if you were to reach out as high as you could get up on a table or a stool or something as high as you could out that window, you're going to be about 10 meters above the ground. Okay, if you were to release the ball from there okay, some type of a object from there. All the energy in that object right before you release it is potential energy. Gravitational potential energy. That would be mgh. Now they don't say it outright here, but it must be a 1 gram ball, okay? A 1 gram object. Maybe one of those masses. Remember, we did them when you were yanking the paper. Those were 20 grams, I think. So if it's a little bitty one, 1 gram, and you had it 10 meters up, M would be 1 gram, 1 kilogram, not gram, kilogram, 1 kilogram. That would be, the ones we had were 20 grams, so it would be 5 of those. That would make 1 kilogram, okay? 1 kilogram mass, 10 meters up, acceleration due to gravity 9.8. So 1 kilogram, 9.8 times 10, that would be 98 joules. Okay? Initially, velocity is 0. You're leaning out of the window there as high as you can go. Your initial velocity is 0. Kinetic energy would be, if your velocity is 0, your kinetic energy is 0, because it's 1/2 mv squared. If velocity is 0, so is the kinetic energy. So all that energy in that mass, that 1 kilogram mass, that could be the book here. That would be about a kilogram, I think. Okay, would be 98 joules, potential energy. You release it. It starts losing its gravitational potential energy because it's falling. But it's gaining its kinetic energy because it's picking up speed. With 5 meters, that would be about midway through the second floor down there. That would then be, it would be about halfway down. So now its potential energy would be half of what it was there, 49 joules. That means the other 49 joules that were up here, they're now kinetic energy. Okay? And from this, you can figure out what the velocity would have to be. Either by this formula, when the height was now 5 meters, you could figure it that way, or you could just take, it's 49, double that, be 98, divide by the mass, which is 1 kilogram, and then take the square root of that, and that would give you your velocity. Okay? Now, at the ground, right before it hits, is kinetic energy. The potential energy is now 0 because you took that as your 0 reference level. That's now 0 height, so that it has 0 potential energy right before it hits. Its velocity would be 14 meters per second. Well, wait a minute, halfway down it was 9.9. Well, remember, the energy is proportional to velocity squared. So you square this, and that's where you get the total energy. You have to square a bigger number up here to get half that amount of energy. Okay? And bigger than twice that, half of that is what I meant. Okay? And then down here, all of its energy is now kinetic energy. That full 98 joules is now kinetic energy. But all through the process, mechanical energy was constant. 49 plus 49 is 98. 98 plus 0 is 98. 0 plus 98 is 98. The mechanical energy was constant, 98 joules the entire flight down. Okay? Total energy, think of that as mechanical energy, 98 joules throughout. Make sense? Okay. It's just about time, isn't it?
Yes.
Okay. So what we'll do before we get the slides and the book are not quite together here. What we'll do next time, leading off, we'll do example 3.9 and 3.10. Okay? That's where we'll begin next time. Somewhere about the same slide. And then we'll get into more energy conservation, energy sources today, and that's pretty much going to wind up the chapter. Energy sources tomorrow, a little bit there. So, today we'll have the first lab in chapter 3. Okay? Thursday, we're basically going to finish the chapter and have the second lab in chapter 3. And that may be the only 2 labs we have in chapter 3. meaning that next Tuesday we'll have the test in Chapter 3. Okay. And we'll get started in Chapter 4 next time also. And we'll get going in that. And then Tuesday of next week we'll probably have the first lab in Chapter 4. I know that one we have, I think it was 3 labs in that. So, any questions what we've done so far in Chapter 3? So, why don't y'all, I'm going to pause this. Okay. Now, nobody step on my computer here when you're doing your stuff. I'll take it with me. So what we're going to do to get the height, what you're going to go is from the floor up there to the floor here. Okay? That's going to be our height. Okay? That we are going to travel. So how you get the height?
The height.
Huh?
So how you get the height?
Okay. What we're going to do is use the foot side of this, not the meter side, the foot side. Okay? Now that will be how many inches in 3 feet?
In 3 feet, 36.
36. So there's 36. Okay? And then you'll put this on top of there and do another 36. That gets you right about there. Then what you need to do is move along here. You know, these are level until you come out here. Okay? And then do another 36. Okay. So you're adding the number of feet. That's 3 feet, 3 feet, 3 feet until you get up here.
So it's 10 foot. What's that? 10
Okay. You have to figure that yourself. Now, don't go to the top of this structure here because the floor is somewhere below that. So you have to figure out from that floor up there to this floor here how many feet. To the nearest foot. You don't have to do it to the nearest inch, to the nearest foot. Okay, you understand that? That's going to give you your height. And on your data sheet here on page 128, then you'll put the vertical height in feet. Okay?
Yes.
Not yards, not inches, feet. Okay? To the nearest foot. You don't have to get it to the nearest tenth of a foot or anything, to the nearest foot. Now, when you're doing the measurement, you're doing the walking or the running, then you put your weight. Now, you ladies, if you want to fudge on that, you can. I don't care. Put a weight down there that's reasonable. Okay? Here.
Our weight?
Your weight.
My
when
weight.
you're doing it. Right.
Okay.
Here, you want you to stick back. Okay, good deal. Now, let me borrow a stopwatch. Someone who has a stopwatch. These are a lot more fragile. Okay. So, some person is doing the walking, another person is doing the timing. The timer gets right here, so he can see when you begin and when you end. Okay?
So we walking or running?
Okay, the first time, each person is going to do it one time walking. A nice, leisurely walk. If you saw me walk up here, that will do for walking. The person up here with the stopwatch, remember, stop is at 10 o'clock, 2 o'clock, and reset is over here at 10 o'clock. So the minute, the instant the person starts, you start it, and you watch them walk all the way up, and when they hit that top step, you stop. Now I just made that up, and that was 6.66 seconds. Okay, so that was that one. Okay, that's the walking. Now let me tell you about the running one, and this is important. Now somebody else has your box, so be sure you get your box back. The running one, there it is. The running one is not as fast as you can go. The running one is as fast as you can safely go. So this will be adequate. If this is your walk, if that's your walk, that's fine. Okay? Then all you need for a run, because I don't want any incident reports. I don't want to have to fill out any paperwork.
If we fall, can we get extra credit?
Huh?
If we fall, can we get extra credit?
You lose extra credit. Okay? You lose every credit. No. Okay. Your run can be something like this. Okay. That would be perfectly fine for a run. Okay? Something faster than your walk. Not as fast as you can go, something faster than your walk. Okay? So, same timer, gets the walk, gets the run. You fill that out for person A. Or Facebook, right there. Okay? Then, you swap people around, and then do person B. Volunteer B. Now that's all you have to do, but if the third person wants to do it, you've got plenty of room in the margins on either side. You can do it for the third person as well. Because notice the weight's not going to change. The height's not going to change. You fill it in every place. The time is the only thing that's going to change. You can put time walking here and time running there. Okay, you've got plenty of space there. Now when you come to do the calculations, that will be changing, so you can do it on either side or something there. But you have either 2 or 3 people per team, 1 timer, 1 walker. You can switch them out, do however you want to. All of you measure the approximate height in feet. Any questions? Were there questions? Okay. Now there's only 3 yardsticks because you're using the yard side, not the meter side. 36 inches. Remember, that's where you make your marks at. 3 feet each. How many up there? To the nearest foot. And when the first 3 teams get done theirs, I'll take 2 sticks to the next 2 teams that don't have them. Those 2 teams can go on and start their timing now and then do their height measurement later. Okay? So if you got a stick, do your stick measurements first. If you got don't have a stick, do your timing measurements first, and I'll get you a stick in a minute. Any questions? Okay, 1 team of 3 people stay here. Who's that team? Okay, 1. Who's else with him? 2. Who else with him? 3. Okay, so the 3 of you are here. The rest of you come down this way, and we'll form another one. I'm going to put this on pause so my battery... Okay. All right. So everybody, okay. Reminder. The questions start on page 126, right? Number 1 requires an answer. Number 2 requires an answer. Number 3 requires an answer. Number 4 requires an answer. Number 5 does too, but you can wait till the end of the experiment to do that. Okay. Everybody got put down something close to your weight, right? Okay. In pounds, right? Okay. Vertical height, you got that closest feet. Some people did a half foot, that's fine. The time you got to walk and to run for at least 2 people, maybe 3. Everybody got that, right? Okay, time in seconds, vertical height in feet, and weight in pounds. Okay, times for walking and running. Now, your work done. What units were they? No. Foot pounds. Feet times pounds is foot pounds. And that's how you got it, right?
Yep.
The number 1, weight in pounds times the feet in feet, okay? The vertical height in feet. That gives you foot pounds. Everybody got that? Okay. Then how did you get your power?
Work divided by time.
Work divided by time. The line just above that, you just calculated, divide that by your time. Either your walking time, if that's what you were doing, or your running time, if that was what you were doing. And then how did you get your horsepower? And, what were the units for your power then?
Foot pounds per second.
Foot pounds per second. That next to the last row there is foot pounds per second. And then the horsepower, how did you get that?
Take that and divide it by 500.
Yeah, take your line right above there, divide by 550, and that gives you your foot pounds per second. Horsepower. Okay. Now, just approximately, what were some of your horsepowers? If you've already done them. If not, that's okay.
0.69.
Second?
0.69.
That sounds like a reasonable horsepower. Was that walking or running?
Running.
Running. What was it walking?
0.37.
Okay, those sound like reasonable. They could be quite different from that, folks. Don't feel like anybody's is wrong but you're going to get something less than 1 probably for walking, and for running something closer to 1 or maybe a little bit above 1. Did everybody get numbers about like that? And that'll be HP, horsepower. And if you didn't get those, let's find out why and work together as a group, figure it out. Or come see me and I'll try to help. Any questions? Okay. So you can continue with that if you want to, or if some of you are super anxious. Yes? some of you are super anxious, you can get started on your test. The test is on Chapter 2. Now remember, I'll say this for people who just got here, but I think you remember from last time. For every test, you can have a formula and equation sheet. Okay? And this is the test on Chapter 2. Now, if you don't feel like you're ready for it, you don't have to take it now, but you'll need to get these 2 tests made up as soon as you can, because the third one's coming up fairly soon. And I'll also get you your other labs for this. Don't turn it in? Huh?
Take 3 of those tests.
No, you can only get one. No. Okay.
It'll be all right for me. Those are the ones that get up. I'm all right.
I think that's 3.
Is multiple choice?
Huh?
Is multiple choice?
Most of them are multiple choice. There's number 7's a calculation, and I think number 11's a calculation. The rest of them are multiple. And number 18 is a calculation. So there's 3 calculations. The rest are multiple choice.
Yeah, you should use the first one.
I believe that's right.
And then divide by
Okay.
weight.
And for those who are on this side, I'll put a little light. Are there any questions on the lab before I shut down the recorder? None? Okay, here it goes.